Okay, perfect. Good morning, everybody. Welcome to the AgRobotics Working Group meeting after a couple of weeks with last week's meeting getting canceled. Good to see everybody back. Um, we'll start off with announcement of a few new members. So from the CSA group, we have Anna Maria Tomlinson. Also from CSA, we have Nancy Bestick. From Neat Leaf, we have Elmar Meyer, and from the Linamar Corporation, we have Brad Baker. And I see that Nancy is on the call this morning, so I'll ask if you might want to give a brief introduction to yourself.
Thanks, Jan, and happy to see many of you that I already know. Nancy Bestick with the Canadian Standards Association. I'm a director in standards. We've been busy in the agriculture and agri-food area with a lot happening around automation, data, and some sustainability items like food loss waste, regenerative agriculture, soil health, and on. So looking forward to joining these discussions and sharing and learning, and happy to meet you all. Thanks.
Excellent. Thanks, Nancy. Happy to have you. Um, Perfect. Then with that, I would like to pass it over to Dr. Slava Adamchuk with the University of McGill, who will be presenting to us today. So please take it away, Slava. Everything, everything good on your end?
Hello?
Oh, there you are.
Yeah, can you hear me?
Yes, we can.
Okay, yeah, good. Then you're going to get started?
Yes, absolutely. Take it away.
Okay, yeah, I was waiting to get some introduction.
Oh, sorry, I just did. Did you something might happen there, you might have missed it. Yeah, joining us today we have Dr. Slava Adamchuk with the University of McGill, who will be speaking to us about some precision agriculture and sensor system research. So please, Doctor, take it away.
All right, thank you very much. So, good morning, everybody. I got brief discussion today, talking about proximal soil sensing, and if there is interest also in plant sensing, I can continue into that topic as well. But I'm just here to discuss some of the developments related to the proximal sensing solutions that actually work for agricultural applications these days. So here at McGill University, our research team, it's precision agriculture and sensor systems. And basically we built proximal systems to measure soil and plant parameters. Also, we work on software to process geospatial data. And we built some turnkey solutions for precision agriculture. So this,
Lava,
yes,
probably not everybody on here has met you. So why don't you take a minute and do the Slava story?
well, That's why I asked if Don already did that.
He just said you were at McGill.
Yes, I'm professor and chair of Bioresource Engineering Department, and been working in precision agriculture for 30 years. Most of work in Indiana, in Nebraska, and we had project pretty much on every continent. So I've got a few illustrations of that, and I've been in Canada since 2010. Teaching GS, instrumentation, precision agriculture courses, and we also had projects pretty much across the country here. So
Slav has spoken in Ontario a lot and is a good friend of a lot of ours. So grateful he's able to come today.
well, thank you, Joe. Nice to see you again. All right, so coming back to the topic, remote sensing versus proximal sensing, the separation is about 2 meters. So if it's sensor is farther away from the target than 2 meters, then it's like satellite, aerial, UAV. Then we're talking at remote sensing. If it's proximal sensing, it means that less than 2 meters, so on the go, on the spot, profiling. In terms of sensing, going back to the what can we actually measure, it comes to all the human senses, so we can look, listen, touch, smell, taste, and that's exactly what we do with different sensor solutions. And also we have at our disposal the entire array of electromagnetic waves. The way system works, sensor is just part of the story. We also looking at every case where maybe do the mapping at detailed topography. Also, we're looking at yield data, also remote sensing data, revealing both vegetation and soil, and we combine it with some lab data and farmer experience. And then there is an entire decision support structure that we're not going to cover today, but it's another topic for discussion, is how to go from there to either implementation of best management practices or variable rate technologies. So in terms of soil properties, what we want to measure: soil and buffer pH, some cations, anions, cation exchange capacity, micronutrients, organic matter, particle size analysis, bulk density, soil water content. And there are some solutions that can tackle specific property much more efficiently than others. And that's a topic for today's discussion. So at this time, popular soil sampling solution is still one of the key elements, and that's where AgRobotics can play a key role to get this process optimized. Traditional sampling is random. Of course, we have several different strategies of intensive sampling, and there is some discussion and scientific merit in terms of which is better. But actually, the state of the art is doing directed sampling, going by soil series, by management zone, and in terms of use of automated equipment, that's actually where we see big potential. So here are some of examples of with automated or semi-automated sampling that we've done over years with different projects. You can georeference individual samples, even individual core that goes in combined sample, and then imply this. This one, a little study where we try to compare different sampling strategies as well as different interpolation techniques. So as we can see, there is a significant difference in terms of error, and yet we are still not very far from just simply field average when it comes to such property as phosphorus, which is relatively stable and still has a relatively high degree of spatial variability. So in terms of a problem, like from this grid sampling, we want to go to something more continuous, like, for example, yield mapping and so on. As I mentioned, digital elevation model or elevation maps is one of essential elements. Some of data can be downloaded. Then we also have LiDAR data, like some of using laser sensing. But these days with RTK GNSS on board of many pieces of equipment, the data is already available, so we can get elevation and we can get all the derivatives of that, like slope aspect, catchment, topography, wetness index, etc. So that's must-have layer when we try to do some soil modeling. Because proximal soil sensing, there is a variety of products already available. They range in terms of mode of operation, whether mobile or static, type of measurement, invasive, non-invasive, done in situ, ex situ, energy, passive, active. Active means that energy is generated by the sensor. Passive is just reading naturally occurring or energy caused by emitted by sun. And inference, that's actually quite important. Do we make direct measurement or indirect measurement? For example, a lot of times in industry now we hear about a soil organic matter sensor. But to this point, there is no such a thing. So it's a indirect sensor where we taken light reflectance, some other type of parameters and just converge it into a proxy of soil organic matter. So, but I'm already jumping ahead of me. So here are some physical properties and also the array of sensor families. So some links are more direct than others, and also some chemical properties and also cross-referenced with different sensor systems. So what's available on market and getting popular use around the world. Galvanic contact resistivity method been like since '82. It's actually Michel Debat from Geocarta in France. It's one of early inventors of this type of technology, and of course, Veris system is well known. The one in the middle, it's Geophilis from Germany. So the idea here is that we inject current in the soil, and we have another pair of electrodes at a certain distance, and we just measure apparent electrical conductivity, so ability of soil to conduct electrical charge, which can be related to a variety of soil properties, like the soil series, organic matter to some extent, moisture content. Depending on the distribution of those electrodes, we're looking at different depth sensitivity curves, so we can do profiling, and that's actually depths of topsoil and so on, being one of critical components. And on the bottom, that's one of systems that we developed here at McGill that can measure at multiple distances. So it's like 15 points of measurements when we try to discretize it, so we can do relatively good profiling. Similar story with electromagnetic induction systems, which Ontario is the biggest global supplier of those systems with Geonic Limited and Dulem companies. Here we're using a couple coils, one to create eddy current and another just to measure it through electromagnetic induction. Again, depending on the orientation of coils, height, spacing, height above ground, frequency of operation. We also look at different depths of investigation. And also some of trials that we use, like for example, this unit, it's scans soil profile by changing angle of system with respect to the ground, and because there is many different implications of how the systems can be deployed. Galvanic capacitively coupled resistivity method, it's another electromagnetic induction, another apparent electrical conductivity measurement system. Here, instead of direct contact, current is brought to the soil through a capacitor. So it's like a coaxial cable, and the conductor inside is one side of the capacitor, soil is another side of capacitor, and that's how the current is introduced. Again, space in between a transmitter and receiver defines the depths of operation. So for quite a few fields that we've been working with, this is our typical mapping structure. So we're using EMI sensor on a sled. We have our RTK setup that we get the topography. So, and it's a relatively stable measurement system. So as an illustration how this can be used, like one of primary usage is improvement of soil survey maps. So like here we can see that the pedology exploration show different soil series, but then electric conductivity map reveals exact boundaries of those soil series. Also, when we compare yield data and electrical conductivity data, if there is a correlation, then we know that change in yield has soil-induced difference, and we can plan our seeding, nitrogen management, and so on based on that information. So this link means that it's something that we can deal with. Capacitance sensing is also quite important element. In this case, we use soil as the electric material, and also the electric constant of soil is in direct relationship with volumetric water content. So like this map is a relatively flat field with the uniform field conditions, but when we mapped it with this capacitor, we actually see water base and pretty much like this area on the west, that's a relatively sandy part of the field, so it stays dry, and that's also can be used for variable rate seeding and some of other precision agriculture scenarios. And like capacitor sensor, like many off-the-shelf sensors for stationary measurement, have relatively decent precision and accuracy parameters. Here, a few years ago, we did some work by putting this capacitor sensor in front of the planter and then just changing seeding depths according to the moisture at planting. So when it's relatively wet, we put seed closer to the ground and closer to the surface, and this way we can optimize emergence. Soil spectroscopy is another important part of soil sensing. So we are talking about visible and infrared, mid-infrared light, and there's some systems that are already commercially available. This is a hyperspectral solution, and there is a variety of like multispectral solution. Technically, from like in 1980s, it was seen that around 660 nanometers, it's like far red part of spectrum. Light reflectance has good correlation with soil organic matter, at least for given soil series. And there is a variety of solutions that can be defined based on this. Some companies these days are trying to use elements of artificial intelligence to build those with what we call pedotransformation function, where they take spectra and convert it into some specific soil properties. And this can be successfully done for like texture, organic matter, even total carbon, in some instances pH, calcium, magnesium. A lot of groups claim to be able to address phosphorus and potassium, but it's still like in very specific environment you can get decent calibration, and whether it's feasible to do on a large scale, it's still one of the key questions. This is one of prototypes that we built for Cruiser Labs. It's a Montreal startup that also uses visible and infrared reflectance to predict variety of soil properties. So some of you might hear about that product. So this setup that we built, it's basically you can you can deploy a Cruiser Labs probe with a press of a button. Mid-infrared spectroscopy, we also did some work with that. This is a sensor that was prototyped for extraterrestrial operation, supposed to be deployed on one of Mars rovers. But we tried it for soil measurements, and yes, we can address some texture properties. But we had one paper looking at phosphorus, and so if it's a very big difference, we can still see it, but as the reproducibility of those predictions is still relatively low. So basically, we wouldn't be able to separate, for example, 10 and 15 ppm. That's the sensor would not be suitable for that type of work. But if you have excessive manure management and you get into hundreds of ppm of plant available phosphorus, then yes, the system can distinguish that. Some of our colleagues using portable FTIR spectroscopy, which is also mid-infrared, to make measurements, and those sensors are actually quite good to look at mineralogy. So they're used by geologists and by some of soil scientists that are looking at properties of parent material and so on. And there is a lot of development in this area. Back in Quebec here, Logiac is one of the biggest service providers, and here developed a product called Laser Ag. Soil samples are compacted with a 20-ton press, then dried. So you got those little bricks, and then they're using category 4 laser to actually burn those little spots, like 24 spots, and get spectra on each of the spots. And through this better transformation function, there is a little better success on predicting variety of soil properties. And I think I have a graph showing some comparative study on that. Unfortunately, like there are some people that trying to use laser-induced breakdown spectroscopy in field environment, but there you have difference in moisture, and it's a quite powerful laser. So there is some precautions how this can be deployed, and it's one of potential developments for the future. In terms of machine vision, now it's quite popular in a variety of industries. Soil, of course, can benefit from that. We just finished another project on this topic with even 200 magnification. We can see quite interesting story about soil. Even this is a tiny worm that happened to be in one of samples. But basically, with appropriate data processing, we can make measurement of soil texture. So it's potential to use in the lab on destructive soil sampling, and we also had a couple studies trying to do it in situ. A smartphone can be a decent soil sensor because, like, you have basically color sensors. So whether it's a Munsell color or you got a calibration to look at all the way to soil organic matter, it's feasible of doing. It's would be a low-cost deployment because everybody has smartphones these days. Of course, soil optics is another important type of technology. Of course, it's not an optical part of spectrum. We are talking about gamma ray. Yes, we're dealing with radiation, but there is no radioactive source here. Radioactive source is soil itself. So there is a crystal. It works like Geiger counter, and it measures. It's very sensitive, so it measures emission of some isotopes. And in terms of soil, the most critical would be potassium-40, uranium, thorium, to some extent strontium, maybe a couple more. But the point is that this, like whether it's total count or potassium-40 count, we can really see a soil texture, mineralogy type of interaction. And with some additional data mining and local calibration, soil optics claims to be able to predict over 12 different parameters. And depending on the site, it could be feasible with the quality of the maps. Maps would be more accurate than if you just do a few samples and interpolate. One technology that less recognized for agriculture, and we just finished one project in Alberta where we had 4 sites with ground penetrating radar data, and some of colleagues in the Memorial University in Newfoundland also working on that. It's radar, like the same that they use in construction and some other fields. That's when we are looking about layering. There is a lot of challenges with tiles.
Slava, are you still there? Slava? I'm not sure if you can hear me, but looks like you've cut out. Oh, looks like he got disconnected. Internet must have gone out or something like that. That's unfortunate. Let's take a minute to see if he can get himself reconnected there. That's never happened before. Sorry about that, folks. All right, let's for the time being, let's move along, and then if he joins back in, then we can sort of pick up from where he left off. Okay, so where does that put us? That puts us so conferences, meetings, field tours, and demonstrations. There are no new ones added. from last week's. However, one that should be added is Canada's Outdoor Farm Show, happening September 10th to the 12th. So that'll be added on for next week. That just slipped through the cracks there. Project updates. So, first update is regarding the outdoor farm show. The working group will have a spot there. So if anyone is in attendance, please definitely come on by, say hello. We'd love to see as many of you there as possible. And then regarding the working group, sorry, Colette, the outdoor farm show is in Woodstock. Just outside of Woodstock. I can add a link to it shortly. This is why it should have been on the agenda, and that's my fault. There we are. Regarding the working group, moving forward, starting next week, we've been working for the last little bit to try to craft a template for some social posts for the working group. So we're gonna try introducing that next week. We're gonna be posting on LinkedIn and Instagram. And each week it'll feature this week's speaker, give a brief summary about what they'll be speaking about. So hopefully that'll start spreading awareness of the group, and things like that. It'll be shared for the time being on the Grove's socials, the Grove at Western Fair District. We'll be sharing it through there. If you do see it, please do share it. We'd like it to have as much activity as possible so we can grow and spread awareness and all that good stuff. Okay. And then funding announcements, opportunities. We haven't had any new ones pop up on our radar since the last agenda. So those ones are all the same. If you do hear of any different funding opportunities, please do send them our way. We're happy to throw them up there. We want everybody to be able to access as much money as they possibly can. Brian Waddy, have you mentioned the Innovate BC funding opportunity? I do not believe that is on our list. Would you like to speak on it for a moment? Let us know a little bit about it.
Sure. Hi, good morning, everyone. My name is Brian Waddy. I'm the Director of Agri-Tech Adoption at Innovate BC, so joining you from the West Coast. I just wanted to share briefly, and then maybe I'll send along an updated program page to Dan for next week's meeting. But we are announcing a new intake of the On-Farm Technology Adoption Program, which is, BC's version of the SCAP innovation funding, and next Tuesday, the 20th. And so that will be for farmers to adopt labor-saving technologies. And so I was interested in sharing that news with this group because it's targeted towards robotics, automation, anything that can impact labor efficiency on the farm. I'd be happy to, have any conversations with folks that have questions about that program and how they can get involved. But yeah, I just wanted to put that on folks' radar. Thanks for the opportunity.
Absolutely. Thanks for sharing, Brian. And yeah, if you have a link to that or some info you want to send my way, then I can add that onto the agenda for next week so people can access that. Matt from Finite Farms just wanted to know if there are target crops for the BC program.
Nope, it's open to all commodity groups.
Excellent. Um, Perfect. So at this point, I'd like to open it up to the round table. If there's anything anyone would like to discuss or inform the group about, questions, queries, the floor is open for any kind of discussion.
I have a question for Brian. Brian, this is Colette with Harvest Corp and Triton. I just wondered, does BC have any requirements for asparagus? For automation and asparagus? I don't know if it's grown in BC, so I thought I'd better ask.
We definitely had a few growers of asparagus in the last intake of our program. It's not like the biggest crop by acres, but it certainly is here.
Great. All right, because our automatic harvester might be something you guys are interested in.
Yeah, if you want to connect with me outside this meeting and share a little blurb, I'd be happy to pass that along to the few growers that I know as well.
Super.
Awesome, thank you. Taylor, go ahead.
Okay. Awesome. Can you hear and see me?
Yep.
Great. Yeah. Thanks, Dan. Thanks for the invite. Sorry I missed my inaugural meeting, or else I would have introduced myself. Hi, everybody. Thanks for, or it's good to see you all. My name's Taylor Bentley. I'm with the Trade Commissioner Service of Global Affairs. Folks may know my colleague Mark Goldfield, who follows or who's been following this since inception and worked with many of you already. I'm joining the Trade Commissioner Service just a few months now, and we've actually added or expanded our support for ag tech as a file. I came in also supporting advanced manufacturing technology, and I've now taken on the portfolio for food tech companies in Ontario, and this is something the regional office for Ontario is doing for the Trade Commissioner Service, but we're also seeing more support for kind of this intersection of, indoor food and beverage processing, in addition to what Mark and the TCS has traditionally supported in the realm of indoor and controlled environment systems, precision ag, and even things like more on the life sciences, like cultured meat, and all of that fun intersections that we get to explore in the ag world. So all this to say that we're going to be presenting soon, so we'll give a better idea of what the Trade Commissioner Service provides and what we can provide both partners and exporting or export ready companies in across Canada. But the immediate deadline I wanted to flag for folks is for our Canadian technology accelerators. So I put in a link, and there is a link in the newsletter for the Singapore and Thailand agri-food tech CTA, and that is closing fairly soon. So next week, it closes August 21st. And we also just opened up the application process for the North American Ag Tech Canadian Technology Accelerator. That's not due until October, so we're going to officially stay tuned. I'm going to my colleague Mark and I are going to specifically email folks out and offer support for this North American Ag Tech CTA. We're just confirming with the organizers kind of how they want to sequence that, because sometimes they like us introducing clients directly to them to talk about it. Sometimes they like to keep things more impartial. Sometimes they honestly just don't have the information about what the partner companies are looking for. So in this case, both Singapore, Thailand, and the North American one, you'll see them talk a lot about the partners. So these are really great opportunities to connect companies with different partners in market. But I'll save all of that. Just wanted to flag that upcoming August 21st deadline. And I'll put my my credentials in the email or in the chat if anyone needs any immediate support with that. But other than that, I look forward to presenting to the whole group soon. Thanks all.
Awesome. Thanks for that, Taylor.
All right. Hello.
Oh, you're back. You're able to join back in.
Yes. Electricity just disappeared, so I'm here in little dark conditions, but I think this through cell phone it works, and I just emailed you the rest of the presentation. So I don't know if you can do we still have time or?
Yes, we do still have some time. We've got about 15 minutes left of our time slot.
That's about what I planned. And then I also wanted to hear any comments or discussion points, because I had this one focused more on soil, but maybe there is some and electricity is back. So I can return to the presentation in just like 2 minutes.
Okay. Perfect. Yeah, we'll wait a couple minutes and hopefully you can rejoin us. While we wait for Slava, Anna Maria, I saw that you had your hand up for a second there.
I did. I don't want to take time away from Vyacheslav, but I will just quickly introduce myself to the group. Thank you, Dan, for adding myself and Nancy as new members of the group. I'm Anna Maria Tomlinson. I'm the Director of Strategic and Cross-Sector Programs at the Canadian Standards Association. So we develop accredited national standards in a variety of areas. And most recently, we've been scoping out the need for additional standards to support agricultural robotics and automation technologies. We are looking at agriculture quite broadly, looking at a variety of topics ranging from the need for standards to support the use of ag data, whether it's through additional tools to better support ag data governance, data privacy and data sharing, as well as ensuring data quality and comparability. So that's work that we are scoping out, and we are pushing forward with the help of collaborative partners. We're also looking at the topic of soil health. So Vyacheslav's presentation today is very interesting to me and to Nancy. And in addition to that, we're looking at AgRobotics and automation standards gaps. And we have our own working group that's been helping us better understand the space, understand the roadblocks that are preventing more, easy adoption of some of these technologies within Canada, ranging from validation of technologies to classification of technologies, whether we're looking at performance or safety features. So that's work that, again, like the previous speaker, we also look forward to presenting to this group and getting some feedback from the folks on this call as to what kind of challenges are producers encountering across the country as they're working with new technologies or looking to embrace new technologies, and where can a group like CSA, who are experts in standards development, how can we support the sector to help you make more informed decisions or provide more clarity and comparability around the data that's generated. So those are some of the areas that we'd like to touch on, hopefully at a future presentation. Thank you, Dan.
Excellent. No problem. Thank you so much for joining us.
Okay, and I think the system is back working well.
We can hear you loud and clear.
Hear me? Can you hear me?
Yes, we can.
Okay, good. So now I'm back at the point where I left just a few minutes ago. Sorry for interruption. Probably aftermath of some of the flooding and related issues. Okay, Mechanical sensor is another family of sensors that have been developed, like looking at soil compaction at different level. So here are some of the prototypes that we've developed in the past. This is one of example where we mapped a site and we can see like old roads and other type of significant changes with soil mechanical behavior that can affect operation and so on. So here are some examples of looking at different treatment plots, like tillage treatment plots. We can also differentiate those. This is one of prototypes that we built that's a deep soil implement that can also identify where is this hard pan and change depths accordingly to save energy. Some people were using microphone to also listen to soil and measure soil compaction of soil texture that way. There is some recent development of using this for also series analysis and so on, like looking at vibration of related to soil metal interaction. Air permeability is also one of important parameters. This is one of early prototype of system built in Truro, Nova Scotia for in-field detection of soil nitrate content. It's another prototype from Australia, from Sweden, looking also at buffer pH and some of other ions. This is probably one of the first systems that I worked on using index table to make wet chemistry measurement in the field. So here we were looking at nitrate, pH again. This is our first prototype for on-the-go pH mapping, which is now available through various technologies and mobile sensor platforms. There's a couple units in Ontario doing this type of work. So we also use the same platform, extending it to potassium, nitrate, sodium. We did some work with phosphate also. As just an example of relatively small field with 1 hectare sampling versus map that we get with machines. So it's much higher density. Normally service providers make about 10 to 15 measurements per hectare when they do the mapping. As a low-cost solution, we also have portable probe where we can also make measurements in situ. That's also for pH, for nitrate. We've done some testing this year with both. Soil scan is commercially available option for in-field measurements of both pH and nitrate also. And on the left here is this our cobalt electrode that we built to look at phosphate, which also still have some challenges. This is our on-the-spot analyzer where we introduce array of sensors for on-the-spot measurements. Now, in addition to physical and chemical soil properties, a lot of attention these days to biological soil properties. So we've done some work with biofilm and looking at bacteria. But when it comes to a soil in situ measurements, normally we're looking at greenhouse gases fluxes, especially CO2, since we have decent sensors for that. And this is one of the first prototype where we had substrate-induced respiration, just basically Salvita test in the field, or we look at CO2 concentration in spore space, which actually been driving force for quite a few follow-up projects. With passive chambers, this is one of examples where we build a network of chambers, and then we look how a special distribution of CO2 emission across the field, and we can see, yes, organic soil can emit more at a certain point of time. So there is a different level of bacterial activity that we can actually monitor. The networks that I mentioned here, it's we got 16 of those chambers. We just spread across the landscape, and on your cell phone you can see what's the difference in terms of CO2 emission, depending on different cultural practice, different type of cultivars, treatments, and so on. It takes about 15 minutes to get those measurements stabilized. Excited about those CO2 measurements, we built a couple prototypes using syringe type. So that's when we actually pump air from the soil, and we use the same infrastructure to pump air into the soil. So when we put air into the soil, we measure porosity. And when we suck air in the syringe and then measure concentration, we measure actually CO2. And there are several prototypes built on that. So the bottom line for today's discussion, there is many different sensors, many different properties that we're interested in learning. It's a maze. So what we are trying to do is combine multiple sensors together. Mobile sensor platform is one of illustrations, and we've done a couple of research projects where we're looking at soil pH, electric conductivity, subsurface reflectance, topography, all done at the same time. And there is a logic here, like pH measures water pH is just current reaction of the soil, whether it's acidic or alkaline, then or reflectance related to organic matter, electric conductivity related to texture and organic matter relate to cation exchange capacity, which relate to percent base saturation. And when we combine it with pH, we got lime requirement. So that's basically how it works. And then we can get a quality lime recommendation. Other combination, mechanical sensor connected with moisture sensor, we can look at bulk density, different prototypes when we did that. So when we combine different sensors, of course, it's become software exercise. And we built also several data processing systems. Our neighborhood search analyst, it's been one of the key elements. It's a type of hierarchical clustering tool that can identify zones in the field based on different sensor measurements. And also we can pinpoint locations where it would be best to take samples, most informative to take samples and run local calibration. So we have the circular area search method that's actually defined best location. In those locations, we can have a profiling tool, so then we can go into three-dimensional modeling of soil. If we have robot, we can deploy, so this is on-the-spot analyzer. We can deploy on-the-spot analyzer in those locations. It's kind of like Mars rover, but in Earth conditions. It's one of later prototypes where we combine several physical properties together. We can also put stationary sensor and monitor dynamic over time. So with this combination of proximal sensing, like very dense map of the field with the network together, we can get like water stress potential map every 15 minutes. So for those who are doing irrigation or so, that's actually one of efficient tool to do that. This graph, this chart shows in general how all of this data can be integrated together to get quality thematic soil maps. And of course, using of new methods like neural networks and random forest regression and so on helps us like improve quality of predictions. Here is probably one of the most important slides for today. It's a comparison of property like cation exchange capacity, where virtually every system, like when we're using these physical soil properties, we can improve measurement. Like those are different fields from Ontario. And this line shows like what the status quo, like when we do average type of prediction. So in cation exchange capacity, doesn't matter what we do, we are going to get better map at the end, like with smaller standard error. With potassium, it's only few fields where we can get better than status quo, and but there are some fields where improvement still can be quite significant. So the final for at least this part of discussion that we have ability to optimize seeding rate, liming rate, some soil compaction measures, soil health, and of course fertilization rate, and there is different combination of sensors and other data that have been promising on achieving that. At this point, I can answer any questions, and I also just because the theme of today is more toward robotics. One of my students just did a presentation at an international conference where we actually show how we can take so it's related to in situ measurement of soil health indicators. So the system itself, it's look like this. So it's on the again hitch, and we put it on a bear cup. It's a electrical automated system built by Z-Tractor in California. And here we have 7 different sensors integrated together. I'm not sure if this will work. Let's see. Yeah, it's kind of works. So we did this test earlier this year. So the system just come to a given location and make measurements. It's like this. So we look at CO2 concentration. We look at torque sensor for the detection of friction between metal and soil. We have penetration resistance to the mechanical penetration, also penetration to the air that we pump into the soil. So this is what I have for today. Are there any questions?
We did have a handful of questions come in through the chat. The first one was from Carl, who asked, he'd be curious to know your thoughts on the work Precision Planting is doing with their planter equipment, as well as their radical soil sampling and analysis products.
Yes, this is a very good question. I didn't work with that specific system by myself, but through our research, we tried different mapping platform, and we found that planter system for row crops is probably one of the most stable platform. You have 100% coverage of the field. You have decent operation speed. So you don't have additional cost. Location of the sensor, it's a little bit tricky. We always try to put one in front of the planter, but depending on complexity of the field, so you don't have a lot of space there. And you, like if you deal in no-till conditions, you grow in BT corn and you're going into corn stubble, so that might be an issue of just like dealing with residue of previous crop and making sure soil is prepared well. So putting sensor inside row planting unit is a good solution. That's actually what they pursue. Soil, like ice scan from various technologies, is moving the same direction. So you still have challenge because there is not much space, and the job for planter is actually to make sure that seed is placed right. So a sensor is an added feature. Like we can add sensors as long as we don't interfere with the main job of the planter. It seems like they are able to achieve it, like within, like you can modify the planter unit itself to give a little bit of space for doing measurement. But yes, with the reliable data, we can adjust rate of the seed, we can adjust depth of the seed, and also depending on the mechanical conditions of the soil, the coverage of the seed. So the idea here is that we want to make sure that we have uniform emergence. By default, when we get in regular field, we see that some places crop emerge later than others because of natural conditions of the place. So by doing this optimization, we can actually adjust it and try to increase degree days where it's possible. And also, like once you have this data, like for example on soil optical reflectance, then you can adjust some of soil applied herbicides, you can adjust nitrogen based on organic matter availability and so on. So there is a variety of processes that can be done after that. Good product. For biological testing, no, I didn't work with nanoporous sequencing pathway, so I cannot answer that question. Okay, wireless sensors. The networks that I showed, we used aerometer, watermark sensors. And here there is no real recipe. It's kind of the same nature as soil pH versus lime requirement mapping. One tells how severe is the problem, and other tells what to do to fix it. With water sensors, it's the same way. We have two parameters that don't always correlate. They relate to each other, but they relate differently for different soils. It's called water retention curve. It's a relationship between volumetric water content and soil metric potential. The reason for that the same amount of moisture in different soil conditions may mean different things for the plants. Like for example, if you take a glass of water and pour it in the sand, then water is readily available to evaporate, for roots to take it on, and so on. But if you put it in clay, in some condition, like it's dry clay, it will just trap the water and plants will still not have any energy to extract. So you have the moisture there, but plants cannot have it available. So that's ability of plants to extract water is measured through soil metric potential. So we are talking about tensiometers, we are talking about gypsum block, we are talking about any type of metric potential sensor, which is actually measures in the units of pressure, like kilopascal, PSI, and bar, and things like that. So that tells us if plant is under stress. But how much water to add to get plant out of stress, then you need to have, how much water you already have. And for that, you need to have capacitor, TDR, and neutron probe, and any other sensors that actually link to volumetric water content. In connection to gravimetric water content, which is like weight-based measurement, it's also has some other additional interfering factors. So ideally, you want to have both. You want to have some means to measure how much water you have in the soil, and another mean to show what the energy requirement to get that water out of soil. The good news is that those sensors are really, really cheap. And they can be installed and communicated with. We recently had a project looking at the ability of communicating through the soil. So sooner or later, we will have sensors that we can just simply put in the soil and make measurement remotely without wire connection. But like for those of you who might involved in the process, a wire can become a source for water to penetrate. So basically, when you have the sensor there, your measurement is different than what it would be if you didn't have sensor in place. So it's something to keep in mind.
Excellent. Thank you so much. All right, we are a little bit over time due to those technical difficulties. Thank you, Dr. Adamchuk, for joining us today and giving us your presentation. Thank you to everybody who stuck around a little bit past time to hear the end of those questions there. Okay. With that,
Well, yeah, so thank you, Dan, thank you, everybody. And I was looking through the notes, and I wasn't quite clear what should be the main topic of discussion. So like this one, that a lot of talks these days. So I choose to discuss more on soil sensing, but plant sensing is another part that we can also address, and also just logistics in terms of different field operations and so on, what can be automated and so on. So if useful, we can continue that discussion.
yeah, absolutely. I can definitely connect with you via email after this, and we can arrange another date to speak on another topic for sure.
All right.
That would be
Thank you very
great.
much.
Thank you so much, everybody. Have a great day and have a good weekend.
Thank you. Thanks.
Take care.
Bye.
Thank you.
Thank you. Bye.